related rates. Story problem. SP. Here is the first story problem. First related rates problem I'm showing you. And this is, a general idea of how to do a related rates problem. Obviously, the introductory related rates video lists out the steps, but this is the first time we're actually going to do a problem. And we're going to use the steps to do the problem. So this should help you, and I'll probably have at least 3 other related rate story problems videos. So feel free to look at all of these. Hopefully they will help you in your related rates stuff. Hopefully they'll help you understand how to do them. This is, this is not incredibly easy question here, but if you think you can do it, then you pause the video and do it if you think you can complete the problem, or if you're if maybe once I get to a certain part, you're like, oh, I can do the rest. Then if you feel like that, you can pause the video at certain times and do the problem. I mean, obviously, I don't really care, but just whatever will help you actually learn how to do related rates questions. That's the most important thing. So you know what's best, so you can do that. But I'm just giving you ideas as for what might be the most helpful. How this video could, help you the most. So this is the first of my related rates actual story problem videos, because the other related rates video, the non-SP one, doesn't have any examples. So all the examples are in these SP videos. So here's the problem. 2 drivers start at point A. One heads north at 20 miles per hour, and the other east at 36 miles per hour. After half an hour, how fast is the distance between them changing? How fast is the distance between the 2 drivers changing? Wow. So we have to find a rate. We're looking for the rate of the distance between the 2 drivers. The rate of the change of the distance between the 2 drivers. That's kind of crazy, which is why it's a related rates question. These are called related rates questions because you have to find a relationship between the rates given here. And I'll talk more about that when we get to step 2. Step 1, if you remember, what was step 1? Step 1 was draw a picture. Step 1 was draw a picture, and this is very important in this instance. So we have like a point, they call it point A, right? 2 drivers start at point A. So there's a point A at which the 2 drivers start at, right here. And then one driver goes north, and the other driver goes east, like that. So we can call, I don't know, I guess it really doesn't matter what we call the different drivers. That's not important. The emphasis isn't on we're going to be talking about the distance the drivers are going and the rates that they're going and, stuff like that. But the actual driver, it's the distinguishing between the 2 cars isn't as important as distinguishing between the distance the 2 cars have driven. So I'm going to use N to denote not necessarily the car that's driving north, but the distance the car has driven. And I'm going to use E to denote the distance the eastbound car has driven. Although sometimes I might just refer to the car as N because it's easier, but that's not the main idea behind choosing the letters N and E. It's supposed to just be to represent the distance. Anyway, here's our little graph. Now we want at a specific time, and it actually tells us, right? It tells us at half an hour, we're supposed to find the distance between the 2 cars. So let's say at a half an hour, the northbound car has gone this far, and the eastbound car has gone this far. We're supposed to find the distance between the 2 cars. So here we go. This is the graph that we've drawn, and this is showing a visual relationship between the two cars and their rates. And okay, I guess that's step one. What's step two now? Step two. Step two is write what you know. Write what we know. And not just what we know, but also what we don't know. But what we do know, what did the problem say? It said the northbound car, headed north at a rate of 20 miles per hour. So we can write this like as this. So remember when we're doing related rates questions, I'm going to use a differential notation because there's so many different random variables that I want to make sure you understand what variable I'm differentiating with respect to. So I want the t to be there. I want you to see this. So I'm going to call this dn dt. This is 20 miles per hour. Always write the units. Always write the units with the numbers that you write. Always write the units. dn dt is 20 miles per hour. So this is the distance n. The distance a northbound driver has gone over a certain period of time. This is literally the rate, the speed at which the northbound driver is going. Okay, we also know that the dt, the speed at which the eastbound driver is going, is 36 miles per hour. So these are our two things that we know, the two rates that we've been given. That's what we know. Now, what do we not know? Don't know. Well, there's a lot of stuff we don't know, but the main thing in particular that we don't know is the distance between the two cars. The rate at which the distance between the two cars is changing, which is what we're looking for. We're looking for that at a specific time interval, but we don't know. So if we call this x, this is the distance between the two cars at some time t. If we call that x, then you could say that dx dt, we don't know it. It's supposed to be a question mark. We don't know what dx dt is, and actually, I'm going to draw a black circle around it because that's what we're looking for. I want to make that clear. That is what we're looking for, dx dt. The dx dt at a particular time interval, at a half an hour, is what we're looking for. Because dx dt is actually a function, and thus, the output will differ depending on what you put in. But we're looking for dx dt when you put in a half. We want the evaluation of dx dt at t equals 1 over 2. Is basically what we're actually specifically looking for. Anyway, so this is what we know, what we don't know. Now, the third step is to determine a relationship between the variables of importance. So let's do this third step. Relationship. Okay. Well, do we know a relationship between our two variables? Well, the whole idea of related rates questions, as I said earlier, is actually determining a relationship between the rates, between the different rates, the speed. So we want to find a relationship between all of these things. Now the problem is that between dn dt, d dt, and dx dt, the problem is that usually you can't find a relationship between rates because you don't know formulas of rates. We don't memorize formulas that have to do with rates, which is why you usually have to think of a formula that involves distances or something, and then you can differentiate it to get a formula that involves rates. So that's why the fourth step is differentiate, because you're expected to find a relationship that has to do with distances, then you differentiate it to get a relationship for rates, and then you can actually go on from there, with step 5, which is plugging in and solving. So we want a relationship between these rates, but the way we're going to do that is we're going to find a relationship between distances. That's the first step, relationship between distances. And I want to make that distinction so you're not like, I don't know I can't find a relationship between dx dt and, dn dt. I want to make that distinction. So I want to go back to this picture. This picture is amazing. Why is this picture amazing? Because it shows us that this is a right triangle. The whole thing that's going on here, it's a right triangle. So the distance that n goes and the distance e goes and the distance between the cars, x, between the 2 points, that's x, right? There's a relationship between these two. The relationship is n squared plus e squared equals x squared. The Pythagorean theorem, super important. You must know the Pythagorean theorem in calculus for random uses like this. So n squared plus e squared equals x squared is our relationship. So now I'm going to write it over here. N squared plus e squared equals x squared. Is this a relationship between the two rates? No, it's not. Rates aren't even part of this. This is only distances, which is why when we get to step 4, we are going to differentiate it. I'm telling you why these steps work and the basis behind why we do them in this order and everything, but I mean, you don't have to realize this. You can just follow the steps and get the right answer. The steps I've done the steps so that you could do this mindlessly, kind of. So the step 4, as I said, was differentiate. So you differentiate your relationship, n squared plus e squared equals x squared. If you differentiate that, notice that this is something that you have to be aware of. You have to know this. There are 3 variables here. There's an n, an e, and an x. Which are we differentiating with respect to? What variable are we going to have at the bottom of our differential thing that you see? Which variable would be over there? And is it going to be n, e, or x? It's actually none of them, actually. It's none of them. It's t. We're going to have t at the bottom. Why? Why are we going to have t at the bottom? Because we're trying to find a relationship between these 3, and t is what everything is differentiated with respect to. Also, the question is asking us for dx dt, and t's at the bottom. T's at the bottom of everything. Everything is about with respect to t. Everything has to do with rates, and t, and frequently you're going to have t. So you're going to have d something dt. Because that is literally, that is what a rate is. A rate has to have the dt thing at the bottom. So if you differentiated this with respect to time, it's going to be kind of weird. Obviously, it's going to be implicit differentiation, but beyond that, it's weird just because we're going to have a bunch of variables now. So 2n, realize we have to do the chain rule here. So you have a dn dt plus 2e sorry 2e, and then so there's chain rule here again also. So dt, right? Sorry. Equals x squared becomes 2x, and then there'd be a chain rule also, dx dt. So this is what your new relationship is once you differentiate it. And what do you know? This relationship here actually does contain the rates that are so very important. And so we have now finally got a relationship of dn dt, dt, and dx dt, as I was talking about on this page. The all-important relationship. We finally have it. Now there's only one other problem. We don't know what N, E, and X are. So, what you would normally do, you go to step 5 for the plug in and solve. So, we need that relationship between the two so we can solve for dx dt. This is what we want to solve for, dx dt. And then once we solve, and then so you can solve for that, assuming that you can plug numbers into every other variable here. In total, there are 1, 2, 3, 4, 5, 6, 6 terms, 6 variable terms, right? So we should be able to plug in numbers for 5 of them, and this is the one we can't plug in for, and then we could solve for that. But that's not true because we don't know what n is, and we don't know what e is, and we don't know what x is. So we only know these two ones. So we can't solve for dx dt like we wanted to because of that. So instead, because we can't plug in and solve, we're going to have to try to find out what n, what e, and what x are equal to. We're going to have to try to find out what they're equal to, which isn't that difficult actually when you think about it. N and E and X are distances. And we know, I'm just going to erase this. I guess I'll keep this here. But we know that distance equals rate times time, right? That's always true. Distance equals the average rate times the time. So, because of this awesome rule, guess what? N is equal to dn dt times t. Because dn dt is the rate and n is the distance. So what does that mean? Well, we know what dn dt is, right? That was given in the problem. What is it? dn dt is 20 miles an hour. Okay, so we can go here and plug in 20 miles per hour times t. The time we're talking about is half an hour, right? That was also specified in the problem. So you end up with 10 miles per hour. That is what n is equal to. Oh, that's good. That wasn't too bad at all. We can also find what e is equal to. E is equal to dE dt times t. So dE dt was 36 miles an hour, right? So okay, that's not bad at all. And the time, of course, is a half hour again. By the way, I should be writing hour here. Then I'm going to make mistakes, like putting hour here in the answer, because this is just miles. This is just miles. This is why I want you to write the units, because then you don't make unit mistakes at the end of the answer. If you wrote your answer as 10 miles an hour, and let's say this was the final answer, and you wrote 10 miles an hour, right, you would get this wrong because your unit's wrong. Because this is a distance. N is distance. How can the distance be 10 miles an hour? Miles an hour has to do with speed, right? If you write your units, like hour here, miles per hour, when you do the math, then you realize hours cancel out, so you're just left with miles. So then, you can just simply write that and know that your units are correct because the hours canceled. So that's why I tell you to do that. It's really important. So I'll write hour here also. When I do that, I end up with 36 divided by 2, which is 18 miles. 18 miles. So we have N and E, and then we can find X. Oh, we don't know what the rate. We don't know I mean, this is true. dx dt times t equals x. This is true, but we don't know what that is equal to. We don't know what dx dt is equal to, so we can't solve for x. Oh, no. Hopefully, if you're smart, you think, oh yeah, the relationship here, the picture showed us this was a triangle. Now we finally have n was 10 miles, and we finally have e was 18, right? 18 miles. So now we can find out what x is by using the Pythagorean theorem. Because this is a right triangle and everything. So everything kind of works out in the end, right? So instead of doing distance equals rate times time, no, let's not do that. Let's instead do the Pythagorean theorem. So remember, n squared plus e squared equals x squared, right? Never forget the Pythagorean theorem. So n squared is 10 miles. Always write the units. Always write the units. E squared is 18 miles. 10 squared is 100. 18 squared is, what is 18 squared? I don't exactly know what 18 squared is. I'll have to do that on the side. I should know this, shouldn't I? 144, 8, 1. So 4, 2, 324. So 324, right, equals x squared, and then you add them together. Not 3. Interesting. Square root of 424. I guess you can simplify that, right? Because you can pull out a 4. Well, you can, because 4 is a factor, you can pull out a 4, then you have 2 rad, whatever. But it doesn't matter, right? If this was our final answer, yeah, we should probably simplify by pulling out pulling a number out of the radical. But this is not our final answer. So I'll do any radical stuff at the end once we get to our final answer. So this is what x, n, and e are equal to, which is what I wanted to show you. So now we can go back to this equation and actually start plugging in stuff like we're supposed to do at the start of step 5, right? This is plug in, and solve for the variable in question. And so 2n dn dt. Now I'm just going to write this down again, right? Plus 2e, right? This is what the formula was, if I remember correctly. 2x dx dt. Okay, and then 2n. So now it's just a lot of algebra, which should be really fun. So 20 miles an hour, right? That was given, plus 2e, which is 18, right? It was 18. No, wait. Yes, it was 18. Okay, my memory is not the best, but yeah, it was 18. Pretty sure. 2x. X was the square root of 400. What was x? Square root of 424. Yeah, times the rate, which we don't know. That's what we're solving for. Awesome. Lovely algebra about to happen. Where are the units for... I don't have any units for square root of 424. I must have lost my units somewhere over here. Yeah, this was miles. 100 was miles. 324 was miles. So the 424 is. Oh, no, no, no. No. It was miles squared. So each of these was miles squared. So this was miles squared. So when we square root it, as we do here, you end up with miles. So the unit is miles. That's funny. Because I'm forgetting to write my units, even though I'm always like, you gotta write your units, can't forget. So, so this is 400, right? 400 miles squared per hour. And 2 times 18 times 36. So 36 times 36. 296. Miles squared per hour equals, well, 2 rad 424 dx dt. Then you add them together on the left side of the equal sign, because you can do that, and you get 1696 miles squared per hour equals, this is miles, 2 rad 424 miles dx dt. Now you can just divide, right? Put this under the fraction bar. So dx dt is equal to 1696 miles per squared, miles squared over hours. Not the best algebra you've ever done, probably. Not the like, oh, I love doing this. This is so much fun. But this is what you end up with. So the units, you have miles squared over hours over miles. So in reality, this is miles squared over hours times, so like miles squared over miles times hours, right? This is really what it is. So miles, so you just get miles per hour, which should be correct because this is dx dt, a rate. So that's how you know that you're doing it correctly. One way to know that you're doing the related rates question correctly is when the units all match up. So you end up with something miles per hour. Unfortunately, I'm not sure what that something is. What's 1,696 divided by 2 over 42? Well, okay, 1696. 2 goes into 1696. 8. 4, right? 4, 8. So 848 miles per hour. And then with the square root of 424. Like that. What does that even mean, though? Right? So if you put this in your calculator, you end up getting, if you have a calculator that, like, does radicals, of course. Wait, what? Wait, what just happened? But if you put this in your calculator, you should get 41. It's a division problem. The radical's in the denominator. If you put that in your calculator, and the square root is underneath the radical, you end up getting about 41.2. At least that's what I got on my calculator. Right? That's what you should get. If you didn't get it, then Yeah, 41.2. Okay, that's what I got. 41.2, which I think that should be right. I'm pretty sure that's right. I did the problem earlier, and that's what I got, and that's what I got the first time I did it. So I got it this time again. So yeah, that's how you do it. So that's your final answer. 41.2 is your final answer. The XDT is 41.2. So how do you do related to race question? You have to do all the crazy, awesome rules. You don't or steps. You don't have to do them, but I think they help. Step one. We've come a long way, haven't we? This was the problem. So step one was the picture. Step two was what we know and what we don't know. Step three was relationship between the distances. Step four was differentiate. Step five was let's actually plug in some numbers and solve for the variable in question. Although we had to do a little bit of this was like before algebra. We were doing distance equals rate times time. We had to do a little bit of that before we could actually get to the plugging in and solving stuff. Okay. There you go. More related rates videos to come, hopefully. There you go.